Hello, this presentation is part of my study on antenna and today's topic is far field zone and electromagnetic field patterns. Let's start by talking about the far field zone. As we move farther away from the antenna, the wavefronts that were originally spherical start to look flat, or in other words, they approximate plane waves. This region where this approximation is valid is called the far field or Fraunhofer region. Now, why does this matter? Because once we are in the far field, the electric and magnetic fields become transverse, meaning they are perpendicular to the direction of wave propagation and to each other. This makes our analysis much simpler. A good way to visualize this is by thinking about dropping a stone in water. Like at first, the ripples are curved and close together, but as they spread out, they look more like flat lines. That's the same idea with electromagnetic waves in the far field. Here in the far field zone, the electric field E, magnetic field H, and the direction of wave propagation are all perpendicular to each other. So it's a perfect example of a EM wave transverse electromagnetic. Both E and H fields decrease with distance. Specifically, they drop off as 1 over R, meaning the farther you go, the weaker the field becomes. Also, the phase front, which was originally curved near the antenna, becomes flat in the far field. This planar behavior is what lets us treat the waves as nice, clean plane waves during analysis. On the right, you can see a visual. E points straight up, H is perpendicular to it, and R is the direction the wave is traveling, all forming a neat right angle setup. Let's connect this to something we all know about. You all know circuits. In basic circuits, you use Ohm's law V equals IR. Now, in electromagnetics, there's a similar relationship E equals eta H, where eta is the intrinsic impedance of the medium. In free space, it's about 377 ohms. If we check the units, E is in volts per meter, H is in ampere per meter, and eta is in ohms. So dimensionally, it all fits just like in a circuit. Now, this intrinsic impedance depends on the medium. So it's calculated as eta equals root mu by epsilon. So, for example, if you have a medium like water which has a relative permittivity epsilon r of around 80, then epsilon is large, which makes eta smaller compared to free space. That's why electromagnetic waves behave differently in different materials. When we deal when we deal with antennas, it's more useful to describe the electric field in spherical coordinates using r, theta, and phi directions. In general, the E field can have components in all three directions like the first equation. But in the far field, something nice happens. The radial component ER becomes almost zero, so we are only left with E theta and E phi, which makes analysis much easier. Electromagnetic fields still depend on the angles theta and phi. This is called angular dependence, but the way they change with R is simpler now. Now let's look at how the electric field behaves with respect to distance or R in the far field. The far field electric field has this from the first equation. There are two important things happening here. First, the um, e to the power jkr term, that's the phase term. It shows that the wave is propagating outward like a spherical wave. Second, the 1 by r part, that's the magnitude. As the wave spreads out over a bigger and bigger sphere, its strength decreases, which makes sense because the power is being conserved across that growing surface. So overall, this expression tells us how both the direction and strength of the wave change with distance. In the far field, the power carried by the wave is related to the electric field using this formula. The power is square by eta. Now imagine a spherical surface expanding out from the antenna. Its surface area increases with the square of the radius, that's 4 pi r square. To keep the total power constant as the wave spreads out over a larger area, the strength of the electric field has to drop. So the electric field E drops off as 1 by r, and since power is proportional to E square, that means the magnitude E square drops as 1 by r square. But when multiplied by area, which grows as r square, total power stays constant. This is how power conservation works in radiating systems. Let's talk about the field pattern, which basically means the magnitude of the electric field at different angles. So we start with the full expression, the first expression. Since both terms have the same E to the power minus j k r by r square by r whole square, so factors, we can factor that out and the simplifies to the second equation. This shows that the magnitude of the field falls off the with distance squared, but the pattern, meaning how the field varies with angle, is captured in these two angular components E theta degree and E phi degree. Now let's talk about the radiation pattern, one of the most important concepts in antenna design. If we normalize the electric field to its maximum value, the distance dependence, that 1 by r square, cancels out. What we are left with is something that depends only on theta and phi, the angles. So the shape or pattern of how energy is radiated by the antenna doesn't care about how far you are. It only depends on direction. And that's what we call the radiation pattern. It's all about angular variation, not distance. So to wrap things up, the far field region helps us simplify a lot of things. First, the electric and magnetic fields we have like clean plane waves. Second, we can ignore distance and focus only on angular dependence when studying field patterns. And third, the power spreads out evenly over the spherical surface, which is why the field strength drops as you move away. And finally, the radiation pattern, which shows how energy is radiated in different directions, is super important. It's one of the key indicators of how well your antenna performs. So that's it. Thank you for listening.